We're now going to take the absolute value of a quadratic function, so we know that's degree 2. We're going to begin by sketching the original function, and then any part that has a negative y-coordinate, we're going to reflect that negative part of the graph about the x-axis so that it becomes positive. So in order to sketch a quadratic equation, we want to get some key points, such as the vertex and the x and the y-intercepts. If it's in standard form, we can get that vertex by either completing the square or using that negative b over 2a, substituting back into the formula and getting the y-coordinate. If it's in vertex form, we can just pull the vertex from that form. We also want the intercepts. We know that x-intercepts occur when y is 0 and y-intercepts occur when x is 0. We're going to begin by sketching this original function, x squared minus 2x minus 3. So right now it's in standard form. I know that in standard form that c value is my y-intercept. It occurs when x is 0, so that's gone. X is 0, that term is gone, leaving me just with that value of c. So we can go ahead and plot that on our graph. And then if I take this function, I'm going to factor that, and it will allow me to get the solutions for x. So we can go ahead and see that when we set this factor equal to 0, x will be positive 3. When we set this equal to 0, x will be negative 1. So those solutions are x-intercepts. So we have an x-intercept at positive 3, and we have an x-intercept at negative 1. I can also take this standard form and turn it into vertex form by completing the square, or you can use that formula. Completing the square is going to be faster in time. I'm going to factor the a value out of the first two terms. Well, it just happens to be 1. And then we're going to take half of this, negative 1, square it, positive 1. And what we add to get that perfect square trinomial, we're right away going to subtract. If I go to factor this, I can see that the square root of x squared is x, and then half of 2x is going to be that negative 1. I can see that I've got 1 times negative 1 is negative 1, minus 3 is negative 4. That means my vertex is at positive 1 and negative 4. So now we can go ahead and plot that point. And then you're going to connect those dots with a parabola. And just quickly check, we know that the vertex lies on the axis of symmetry, so that needs to be halfway between those x-intercepts. Make sure that everything looks good. And now that we have the original function, we're going to reflect any negative y values so that they become positive above that x-axis. So let's begin by saying, okay, right now we know that negative 1 and this part of the graph here, that lies above. So that's the original function that when we take the absolute value is going to stay there. And then the same thing, when x is positive 3 and all of those values above, that's going to stay there. It's the bottom part that when I take the absolute value is going to reflect. So right now, I can see that the vertex is at 1, negative 4. When I take the absolute value of negative 4, it's going to become positive 4. So the x-coordinate stays the same, the y-coordinate becomes positive. So we can go ahead and put that point there. And then knowing that every other point is going to reflect, right now my y-intercept is at negative 3. When I reflect, it's going to become positive 3. So using what we know about how the parabola is symmetrical, we can go ahead and kind of fill that piece in there. So right now, this becomes the absolute value of that quadratic function. So we've replaced that original function with a dotted line to show that the absolute value is now going to be this one. Now there's some pieces of information that we're asked to state for that absolute value function, beginning with the intercepts. So we can see that the x-intercepts did not change. So they're still going to be at negative 1 and positive 3. And if points don't change from the original graph to the new graph, we call those invariant points. So they are not varying, they're staying the same. The y-intercept we can see is now going to be at positive 3. We're then asked to give the piecewise function. So when we take the absolute value of this, if we get the same thing, so if this is a positive value, we can see that my line in blue here, that's the part of the graph that is not changing. So if this is positive, the graph stays the same for all values of x that are negative 1 or less than negative 1, that are positive 3 and greater than positive 3. If this piece is negative, we take the absolute value and we get the opposite function. So we get a vertical reflection. It's going to reflect over that x-axis, and that's going to occur for all values of x in between negative 1 and 3. The domain of that graph, we can see it's going to continue on forever. So x is just going to be an element of the real number system. And then the range, we can see that our lowest point on that absolute value graph is 0. So y is going to be greater than or equal to 0, and y is an element of the real number system. Sometimes on this second function down here, people distribute that negative in which case you would end up with this quadratic. So again, these are the pieces of the function for the domain that we're looking at. So if we're looking at all values of x less than or equal to -1 or 3 or greater, this is the quadratic that we're graphing. If we're looking at all values of x between -1 and 3, so this part of the graph here, this is the graph that we have. So we now have a y-intercept at +3, and our parabola is now opening down. All right, we're going to try one more here. So we need to first of all sketch that original function. So I'm going to begin by getting my key points. So I can see that I have a y-intercept at +8, so we can go ahead and plot that. And then we can factor this to get the x-intercepts. I'm going to take out a greatest common factor of -1 to make it easier to factor. And then two numbers that multiply to -8 and add to -2 are going to be that -4 and +2. I can then set each factor equal to 0 to get my solutions, and I can see that x is going to be +4 and -2. Those are my x-intercepts on that original graph. Plot those points, and now we can complete the square to get the vertex. So I'm going to divide a -1 out of those first two terms. Half of -2 is -1, squared becomes +1, and again, what we add in to complete that square, we also subtract right away to not change the value. So I'm going to now factor my perfect square trinomial. So square root that first term, and then it's half of that second term. And then we can see that we have a negative times a negative is a +1, plus 8 is 9. The vertex is going to be at +1 and +9. So then we can go ahead and plot that point. Connect the dots into a parabola, and that gives us that original function. Now when we take the absolute value of that function, every piece where y is negative needs to now reflect so that it's going to be above there. I'm going to leave this original piece that has a y coordinate that's either 0 or positive. I'm going to keep that in blue, and then we're going to flip that up. And now we're going to go ahead and state those key pieces of information that we're asked to state. So in that absolute value function, you can see my x-intercepts are not changing. They're still going to be at -2 and +4. My y-intercept in this case is also not changing because I originally had a positive y-intercept. On the absolute value graph, it still will be at +8. As a piecewise function, we can see that this was part of the original function where y was positive. That occurred between -2 and +4 for the domain. So we're going to have this piece of the function for that part of the domain. We have the opposite function when x is less than -2 or when x is greater than 4. Our domain, x is an element of the real number system, and our range, y will be greater than or equal to 0, and y is also a real number.